Okay. So so ground to ground. Uh, when we're talking about ground to ground projectiles, you guys, once again, what we're really talking about is we're talking about projectiles that are they if we're on the ground, they're starting on the ground, they're going up, and then they're coming back down. Okay. So think about you throwing a ball to your friend. Think about a basketball pass. Um, you know, or even it could be just you throwing a ball to a dog, right? Any of those things. So those would be examples of ground to ground projectiles, right? Now we're going to use all of the same equations for ground to ground projectiles that we use for the cliff problem. So these are the same ones you already know. In the x direction, we have one single equation. That one equation is that Vx equals dx over t. Now, I looked at a lot of your graphs for your lab groups, and when you graphed, with the video analysis, when you filmed the projectile, and then you graphed the velocity in the x direction, almost all of your graphs looked pretty much like this, right? And the reason they look like that is because velocity in the x direction, if this was velocity and this was time, velocity in the x direction does not change. It shouldn't change. And so that graph would be pretty flat. The only reason it wasn't exactly flat is because you guys aren't perfect, right? Nobody's perfect. And you may have had difficulty marking the ball a little bit. But all the ones I saw looked pretty flat. All right. So in the x direction, Vx equals dx over t. And remember, dx is called the range. And t is the time in air. All right. Then we have Vfy equals Voy plus gt. dy equals Voyt plus 1 half gt squared. And Vfy squared equals Voy squared plus 2g times distance in the y direction. And remember, those are all of our acceleration equations because in the up and down direction, in the y direction, we are accelerating, and we're accelerating at 9.8 meters per second per second. In all of these problems, you guys, we're disregarding air resistance. So we're pretending that air resistance doesn't exist. Okay? So I want to revisit this problem, or just thinking about this situation from the first unit. Okay, remember I told you that we can't ever forget our physics, right? So I have a ball, and I throw a ball like pretty much straight up in the air. Okay, so it goes up, 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 hits this point, comes back down, 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 down.
Mr. Bowman,
Yeah.
Marilyn is trying to get in.
Oh, thank you. I appreciate that. I didn't see her. Okay. Oops. I don't want to remove her. I want to admit her. Thank you. I appreciate that. So anyway, I'm sorry. So let's go back to this situation, right? We throw a ball. We throw it pretty much straight up in the air. It goes up, 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 hits this point, and then it comes back down. Okay? Now, what do we know about this situation? Can someone tell me a few things that we know? Nobody? Here, I'll throw out one thing. Okay? So I'll write down one thing. We know the acceleration. We know that's 9.8 meters per second squared. So on the way up, this ball is getting 9.8 meters per second slower every second. On the way down, this ball is getting faster 9.8 meters per second every second, right? So we all knew that. That was an easy one. How about, let me ask you this. What about the speed? So I have the starting speed of the ball. right? The starting speed when I throw it, we'll call that the initial velocity. And then I have the final speed right before it hits the ground. How do those two speeds compare with each other? And I know someone wrote something, but I can't see it. I'm going to... so would it be that the y is constant for both? Well, kind of, yeah. Um, but they're not both zero, right? Because I'm taking this ball and I'm throwing it up with some sort of speed. And then as it goes up, it's losing that speed 9.8 meters per second every second till it hits this very top point. Then it starts coming back down. And so it's gaining speed at 9.8 meters per second every second. So how does VO compare to VF? The speed that I throw it up at to the... Did someone say something?
No.
No? So nobody has any idea how the original velocity here would compare to the final velocity?
Wouldn't they both be the same?
They have to be the same. Thank you. So the speed that I throw it up at is going to be the speed that it hits the ground at because it's losing velocity at the same rate that it's gaining it. So when it goes up, it's losing it at the same rate that it's gaining it on the way down, right? The acceleration is negative 9.8 on the way up, positive 9.8 on the way down. So if it left my hand at 9.8 meters per second, that means at the end of 1 second, it would have lost all its speed. It would be at zero. And then as it falls, if it took a second to go up, it takes a second to go down. And its speed right at this point will be 9.8. Then the other thing that we know, and we talked about this before, we did problems like this. I don't know if you guys remember this, right? At that one place, at the peak right there, for one moment in time, the velocity at that moment is zero. So for one brief moment in time, when the ball hits the topmost point that it's going to get to, it's actually not moving. It's frozen for an instant. Then it starts falling again. Hopefully that makes sense because as it goes up, it's getting slower till it stops. Then it's getting faster till it hits the ground. So at that point, the velocity is going to be zero. I know that the speed that it's thrown at will be the same as the speed that it hits the ground. I also know that the time that it takes to go up, that's going to equal the time it takes to fall back down, right? Once again, because the acceleration on the way up is the same as the acceleration on the way down, or I should say the deceleration on the way up is the same as the acceleration on the way down. So it slows down at 9.8 meters per second on the way up. It's going to speed up at 9.8 meters per second on the way down. So the time on the way up is going to equal time on the way down. Does all of that stuff make sense so far? Give me a thumbs up or okay in the... Yeah, okay, I got some thumbs up. All right. So now, that's if I throw a ball almost straight up and it comes almost straight down. So now let's think about our cliff problem. There are certain things in our cliff problem that we always know to be true, right? So because in our cliff problems, we're shooting this thing out horizontally, we always know that the starting speed in the y direction is going to be what?
Zero.
It's going to be zero. It's always going to be zero. We always know that this thing will accelerate at the acceleration due to gravity because, right, we're pretending there's no air resistance. So the acceleration is always 9.8 meters per second squared. In fact, if we go back and look at our equations, we don't even write acceleration. We write acceleration due to gravity. We write little g, right? Because we know it's always going to be 9.8. The other thing that we know, you guys, that in this problem, okay, in the y direction, So in the y direction, velocity increases, right? So as this projectile falls, it's picking up speed in the y direction. And we also know that in the x direction, velocity is constant. It does not change. It's always the same. All right? So we're good still so far? Okay, and this is all stuff that you saw in your lab. In your lab, for part 2, when you made a graph for Vy, you saw that it was linear. Your Vy graph looked like that. Why did it look like that? Or if you didn't change the axes, it looked like it was going down, right? That's fine too. But the reason that velocity versus time looked like that is because you were increasing by 9.8 meters per second every second. If you had taken the slope of that line, it would have been 9.8. And then if you had taken the slope of the x one, it would have been 0 because the velocity is constant. Or it would have been really close to 0. All right, so those are things that we already know. We figured them out in our lab. We've done problems on them. All right. Now, for ground-to-ground projectiles, they're going to go up, 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 and they're going to continue forward. So basically, you guys, what a ground-to-ground projectile is, it's kind of a combination of the first 2 things I showed you. It's kind of like a cliff problem in that the projectile that we have, right? The projectile is always moving forward, all right? And because it's always moving forward and there's no forces from side to side, velocity in the x direction, that will be constant. It will not change, okay? Just like it did for a cliff problem. So in the x direction, the velocity is never going to change. Always be the same. Now, it's kind of like when I throw a ball straight up in the air. So when it goes up, it's going to lose speed in the y direction at 9.8 meters per second every second until it hits this topmost point, and then it's going to start falling and gaining speed at 9.8 meters per second every second. All right? So in the x direction, the velocity is constant. In the y direction, okay, acceleration is going to equal 9.8 meters per second per second. And it'll equal negative 9.8 on the way up, positive 9.8 on the way down, right? At this very top point too, when the ball gets to that very top point, in the x direction, it's still moving forward, but at that point right there, what's velocity in the y direction? So it's going up in the up and down direction. It's losing speed at 9.8. It's losing speed at 9.8 meters per second every second until it hits that one spot where it's moving at 0. That's right. So at that very top point, in the y direction, the speed will be 0. So it was losing speed in the y till at that one moment in the up and down direction, it won't be moving, and then all of a sudden it'll be picking up speed again and falling. So we know that at the topmost point, velocity in the y direction 0. All right. So I know that. I know that in the x direction, Vx is constant. I know in the y direction is always accelerating at 9.8 meters per second towards the Earth. All right. So at this point, you guys, I just want to show you. I want to show you a little video. And I told you there would be lots of sports videos in this. So this is another one of those. So let me play this. It's not very long.
With more than 1,000 punts over a 16-year NFL career, Craig Hendrick knows down to his toes the secrets of a perfect punt.
When you make contact with that ball, it's almost a feeling that you don't feel the ball in your foot. It's almost like you're swinging your leg in air when the ball comes off of there perfectly.
Elite kickers like Hendrick have been known to launch a football 120 feet in the air at speeds of up to 90 miles per hour. These powerful punts are a perfect example of projectile motion. And the arc the ball makes as it slices through the air is something that has been studied by scientists for centuries, all the way back to Galileo Galilei, one of the great thinkers of the Renaissance.
He's one of the first people in Western science to realize that the shape of that curve is something the mathematicians had been talking about for a couple of thousand years. It's called a parabola.
To help us understand projectile motion and parabolas, we asked Hendrick to perform his craft in front of a super high-speed camera called a phantom cam. It all begins with the drop.
And action.
The ideal drop, the ball has to stay level, or with the nose or the front of the ball slightly up. At the moment of impact of the ball, our leg will actually snap and actually straighten out at that moment, and that's the exact moment that you want to make contact with the ball.
And up it goes, following a path and the laws of gravity.
Once a punter kicks a football, it becomes what we call a projectile. And it follows a path that we would also call a parabolic arc or a parabola.
As the football flies through the air in the shape of a parabola, there are two main components of velocity affecting the ball.
It has a horizontal component, the speed it's traveling along the ground, and a vertical component, the speed it's moving vertically.
These two velocity components, the vertical and the horizontal, can be
So you guys, just so you know, we've been calling the horizontal Vx, you know that, and the vertical Vy, same thing.
Presented as vectors.
A vector is basically an arrow in 2 dimensions that describes some kind of physical quantity.
In this case, vectors show the physical quantities of speed and direction. The greater the speed, the longer the velocity vector. As gravity tries to slow the ball down, the vertical velocity vector gets smaller.
Gravity is acting on it from the instant that it leaves the player's foot, but the effect of gravity is demonstrated by the fact that the speed of the ball is decreasing.
Gravity eventually causes the football to stop rising and reach the top point of its trajectory.
When it's at that high point, something very curious goes on. It has no up and down speed at all. And so the up and down speed of a ball at its maximum point of arc is 0.
Our goal in punting is to get the ball to hang in the air, to be in the air as long as possible.
And then it begins to come down, and the speed goes from 0, and then it comes back down really fast.
Gravity pulls the ball back down to Earth. As it gains more speed, the vertical velocity vector now points downward.
When it starts to come back down to the ground, the vertical component of velocity is in the opposite direction and the horizontal component is still the same.
And down it goes until it reaches its mark.
It was always a great feeling to get as a punter to watch that ball go in the air knowing that you'd hit it perfectly.
Parabolas come in all shapes and sizes, but it takes NFL punters like Craig Hendrick to turn science into an art form.
All right, so basically, you guys, that just explained what we've been talking about right here. And that is at this point, as they were saying, the up and down velocity 0. As the ball goes from left to right along this path, so as the ball is going from here, Vx never changes, always constant. And then in the y direction, it's getting smaller and smaller and smaller, the velocity, until it hits 0, and then it's getting bigger and bigger and bigger. All right. Now, because of that, just like our original problem, the starting velocity, the velocity that the ball in the video, the velocity that the ball was kicked at, right? We'll call that V initial. And the velocity that the ball hit the ground at, we'll call that V final. They will be the same. So this velocity will be exactly the same as this velocity. And the launch angle here will be the same as the angle it hits the ground at. So when I say the velocity is the same, I mean the speed and the angle. So now, if that's true, right? If this velocity is going to be this velocity, then this is how we're going to solve these problems, all right? We are going to pretend that this is a cliff problem. We're going to pretend actually that this part doesn't exist. And we're going to pretend that the ball started at the peak and then fell. All right? Because at the peak, velocity in the y direction will be 0. We'll pretend that's original velocity. And then when it hits the ground, oops, I grabbed the wrong thing. When it hits the ground, this ball, the velocity that it hits at will be the same that it was launched at. So if I know the original velocity, we're just going to call that the final velocity. Now the only tricky part to this is that when I solve this problem like that, half of the time, I didn't mean to use that. Half of the time that the ball is moving, right, it's going to be going up. Half of the time that the ball is in the air, it's going to be coming down. So if I were to break this into half, right, and pretend that it's a cliff problem, when I'm solving for stuff in the y direction, I'm always going to use half of the time that it's actually in the air. But when I solve in the x direction, I'm going to have to use the whole time, not just the half of the time. And so we can see how that's going to play out. Let's do a problem together. So is it all right if I go to the next slide? Okay. So, and I'll post all this, all right? So here's our problem. I have Jose Abreu, he hits a home run. Now the launch angle of this home run is 28 degrees. And the speed of the ball off the bat is 50.5 meters per second. I want to know a few things. I want to know how long is the ball in the air? How high does the ball reach above the ground? And then what is the range of the ball, or how far does the ball end up from where the batter hit it? So let's kind of draw this out, what this would look like. And I'm not the best at drawing. Okay, so this is my situation, all right? I want to find dx. I want to find out the range. How far did that ball end up from the batter? I also want to find out dy. Okay, so dy is going to be how high did the ball get above the ground? And then I want to find out the time. The total time in the air. So to figure that out, you guys, I need to know a few things. First of all, I have to remember that the velocity that the ball is hit with, the velocity at the very beginning, that is going to be equal to the velocity that the ball hits the ground with. So that's always true, right? Unless, so the only time that wouldn't be true is if I launched a ball off a cliff at an angle and it went into a valley. Now we're not going to do those problems. You guys, we don't have time to do them and still cover other physics. So for this class, it's always going to be true. If I'm launching on level ground, it'll always be true. So my final velocity, the velocity that the ball is going to hit with, is going to be 50.5 meters per second, and it's going to hit the ground at 28 degrees. All right, if I were to draw that out with vectors, I have my ball landing, right? This is the actual final velocity. And then I'm going to draw in, this would represent final velocity in the y direction. That's supposed to be straight. There we go. And then this would represent velocity in the x direction, which never changes. Okay? So this would be VF. And we know in this problem VF is 50.5 meters per second. This part is Vx. And then this part is VFY. Now I did a bad job of drawing this because this angle is going to be 28 degrees. And I'm pretty sure that you can tell I drew it bigger than 28. So in reality, Vx is going to be bigger than VFY. My triangle is out of scale. Now, how would I find out what Vx and VFY is? You guys know some math that would let you do it. Yeah, we could use trig, right. We're going to use our trig functions here, all right? So, we know the hypotenuse. I know the angle. For Vx, you guys, Vx is the adjacent side. So which trig function has the adjacent side and the hypotenuse? Cos. So if I want to find Vx, Vx is going to be the hypotenuse, which is 50.5, times the cosine of the angle, which is 28. So if I plug that in my calculator, can someone do that for me?
$51.2.
Okay, that sounds right.
Oh wait, I plugged in the wrong number. Hold on.
Oh, okay. All right. Oh yeah, it can't be 51.
Yeah, I was just like, wait. It's 44.6.
Okay, there you go. So 44.6, and then for VFY, that is the opposite side. So we'll use sine. So that'll be 50.5 times the sine of 28.
$23.7.
22.7.
23.
23. All right, 23.7 meters per second. So you can see, once again, I told you I drew that out of scale. In the x direction, speed is 44.6. It stays at the whole time. In the y direction, the final velocity in the y direction is 23.7. Now the reason the x direction, the velocity is so much bigger is because this angle is fairly small. So now, why did I want to know those two things? Well, this is a lot like problem number 3 on the first cliff problem set. So if you guys tried that, I gave you the final velocity and you had to use trig to find the y and the x. Okay, I need the y because I have to find out the time. And basically, you guys, this is what we did. We're pretending that the ball started up here and landed on the ground over here. Okay. And that this final velocity, this VF, is 50.5 at 28 degrees. So if we pretended this was a cliff problem, right? What we're going to say that the original velocity in the y is 0. And I could use this equation to solve for time. VFY equals VOY plus gravity times time. And so I know 23.7 meters per second equals 0 plus 9.8 times t. And to get t, you divide both sides by 9.8 because that 0 just goes away. And I will get 2.4-ish seconds. I don't know exactly what.
2.42.
2.42. So 2.42 seconds. Now, because we pretended that was a cliff problem, we didn't solve for the time, you guys. What we solved for was, I thought I could just move the parenthesis. What we actually solved for was half of the time. We solved for the time it took to go from the peak to hit the ground. Does everybody understand that? So in the y direction, for these ground-to-ground problems, for the y, we're always going to use half of the total time. And when we solve for things, we'll always be solving for half of the time. So the actual, right, if half of the time was 2.42 seconds, that means the total time in air was 4.84 seconds. So it took 2.42 seconds to rise up to get to the peak, and then it took another 2.42 seconds to fall and hit the ground. So total time in air, 4.84. We use half of the time anytime we're doing any part of the problem we're solving for y. We use the full time for any part of the problem that we're solving for x. Because the x, that dx, right, the velocity is not changing, and we need the whole dx, not just from the peak to when it hits the ground. So for how long is the ball in the air? It's actually 4.84 seconds. Now for how high does the ball go? Because that's in the y direction. In the y direction, we're going to use this half time, 2.42. So we'll use this equation, that dy equals voyt plus 1/2 gt squared. And we don't even have to do algebra. That's going to be 0 plus 1/2 times 9.8 times 2.42. I can't write units because I didn't give myself enough room. I'm sorry. And I just plugged that in my calculator. Oh, 2.42 squared, by the way. So can someone plug that in and tell me what the answer is?
I'm getting 28.7.
That sounds right. 28.7 meters. So that is dy. That is how high the ball got above the ground. To give that some perspective, you guys, that's a little taller than a 9-story building. All right, so it went up. It went up a pretty good amount, but you know what? It went forward an even higher amount. So far, is everybody still with me? Do you have questions before I do the last part? Okay, I'm gonna assume that that's we're still with you. Yeah.
Why do you use 2.42 and not 4.84?
So okay, because what we're doing here is we're pretending that this is a cliff problem. And the reason that we're pretending it's a cliff problem is because we know how to solve those, right? And if the ball right there at the highest part of its path, if we know that the speed there is 0 meters per second, then it's literally like a cliff problem where the ball is being fired horizontally, right? Because for that one moment, it's not falling up and down, it's just moving forward.
Oh, so you don't need that to happen.
Right. So we need to do the half time. But then for the x direction, I can't use the half time because I don't want to know how far it went from here to here. I want to know how far it went from the very beginning to the very end. So for the X direction, we have to use that full time. This is the part that you guys are going to get most confused on the test. This is the part that people make the most mistakes on. All right? When to use that half time and when to use that full time. In the X direction, always use the full.
On the test, do we clarify that we're using half time or the full time or no?
Right. Well, so if it's ground to ground, if it's a ground to ground problem, in the Y direction, you always use the half time. Right? So that's how you'll know. Right? And then, so you guys, for dx, we only have one equation in the X direction. It's Vx equals dx over t. So you know that algebra, the dx is going to be Vx times t. So if I take the Vx, which we already found over here, 44.6, and then I times it by the time, and in the X direction we have to use the whole time, that will give me the range. It'll give me the distance it fell from the person hitting the ball. Can someone tell me that?
Wait, isn't it Vx equals dx over t?
It is. So here, do you mind if I show you something really quick? So Vx equals dx over t, right? And if I wanted to solve for dx, I would have to get rid of the t. So what would I have to do? Right, I would have to multiply both sides by t, right? Because that's being divided.
Oh, okay.
And so those will go away. And then so it'll end up with being dx equals Vx times t. So what I did, I'm sorry you guys, I just did the algebra because I was running out of space. Normally I would have done the algebra, but I just don't. I'm filling up this poor little slide here.
Also, so when we're looking for the range, do we always use the full time then too?
Yeah, you always use the full time in the range because that'll be from the batter or, you know, from where the projectile was launched to where it hits the ground.
Okay.
So can someone tell me what that is here?
Uh, 213.86.
All right, 213.86, and that will be meters. So to kind of put that in perspective, you guys, that would be roughly 700 feet. That would be a really monster home run, okay? In reality, in the real world, the ball wouldn't reach that far. Can anybody tell me why?
Like air resistance?
Yeah, it's because of air resistance. So in the real, if we pumped all of the air out of the stadium, that wouldn't be easy, right? You couldn't actually play baseball then. But let's say that we could do that. The ball would actually travel 700 feet. Now, if you watch a baseball game, they'll show you the stats right on the screen. So they'll show you the exit velocity. They'll show you the launch angle. If you couldn't figure it out, like I didn't make those numbers up. That was from Abreu's longest home run last year. Okay. So that was the actual exit velocity. And then he only hit that ball. They projected that it only went 462 feet. That's because of air resistance. If there was no air resistance, it would have gone, 213.86 meters, which is over 700 feet. So we're in pretend physics world here. We're pretending there's no air resistance. Now, if you guys watch baseball, or football or any other sport, soccer, they make a really big deal about launch angle. So whether you're hitting or whether you're trying to kick something far or whether you're trying to throw a pass, they, like in football, they'll always talk about the arm angle of the quarterback. They'll talk about the launch angle of the punt or the kick. In baseball, they talk about the launch angle off the bat. Now, the reason for that is because if I launch a ball at, say, an angle of 10 degrees, okay? Here's my ground. Oh, I want flat ground. I'm actually going to use the lines. I'm sorry. Okay. So here's the ground, okay? Now, if I want to launch a ball, or if I do launch a ball at, say, 10 degrees, 10 degrees would be a really shallow angle, okay? Do you see that almost all of the velocity is going to be in the x direction, very little will be in the y, so it won't go very high. Do you see that? Now, I could think, okay, you know what? That was a bad idea. I'm going to launch my projectile with a much bigger launch angle, okay? So I'm going to launch my projectile with an angle of 80 degrees. So this would be more like 80 degrees. And if I launch this with 80 degrees, that's almost straight up, not quite straight up. If you see 80 degrees and 10 degrees, they give me the same result. Because in the 80 degrees, I have way more of my velocity in the up and down direction, so I get way more time in air, but I actually end up with the exact same range because I have very, very little of my velocity in the x direction. So at 10 degrees, almost all my velocity was in the x direction. I didn't get very much time in air, but it gave me the same range because it was going so much faster in the x direction than the 80 degree punt. So 10 and 80 will give you the same range. 80 will give you more time in air. 70 and 20. If I kick two balls at those two angles with the same speed off my foot, they will have the same range. Does that make sense to you guys? 60 and 30, they'll produce the same range. 60 will have more time in air. What angle do you think would be most advantageous for producing the longest range? Maybe an angle. Oh yeah, I just saw it. It's 45 degrees. Oops, that is not what I wanted. So if I launch something at 45 degrees, right? What I'm doing is I'm making sure that I'm maximizing the x component, or the forward velocity, and the up and down velocity. All right? So 45 degrees, you guys, that gives you the maximum range. 45 degrees always gives you the maximum range. If you deviate from 45, the range will be less. The more you deviate, the smaller it'll be. Okay? So if I deviate like to 0 or 90 degrees, that will give me the smallest range. Because if I have 0 degrees and I kick the ball, it's never in the air, so the range will be 0. Or if I have 90 degrees and I make it go exactly straight up and it comes exactly straight down, it didn't go forward away from me, right? So 45 is maximum range, like 44 or 46. That would be like the next closest. The further you move away from 45, the smaller the range gets. So there are times when you might, say if you were an NFL punter, you might not want to always kick the ball at 45 degrees. Because if you kick the ball at 45 degrees and you kick it really hard, if you ever watch football, they call that out-kicking your coverage. So the guy catches the ball way before the other guys can run down the field. And a lot of times the receivers are good enough that they can find a way to the end zone, right? So usually those guys don't kick at 45. They kick not quite at 80, but they kick the ball a lot higher up than they do forward. And hang time depends on that angle. The closer you are to 90 degrees, the bigger the hang time. The closer you are to 0, the smaller the hang time. The closer you are to 45, the bigger the range. And then these angles like 10 and 80, they complement each other. Or 30 and 60, 70 and 20, 15 and 75, right?